Alex Bayen is the Liao Cho Professor of Engineering at the University of California, Berkeley, in the departments of Electrical Engineering and Computer Science, and the Department of Civil Engineering Civil and Environmental Engineering. He's the director of the Institute of Transportation Studies and is a faculty scientist in mechanical engineering at the Lawrence Berkeley National Laboratory, where he is also the director of the Transportation Initiative. Dr. Bayen has worked at NASA and at the Department of Defense in France, where he holds the rank of major. He has published 2 books and over 200 peer-reviewed journal and conference publications. His research has been covered hundreds of times in the mainstream media. Dr. Bayen is the recipient of several awards, including the P. Case Award, the IEEE Antonio Ruberti Young Researcher Prize, and the Gilbreth Lecture established by the NAE. Please help me welcome Dr. Bayen.
Thank you very much for the invitation. I'd also like to thank Horst, Simon, and Esmond for being here today. I'm going to talk about a very different topic, but which also uses a lot of large-scale computing, both cloud and HPC, which is routing and inference in transportation. So if one remembers the maybe first controls class you ever took, if you try to regulate any process, in general, you have actuators, you have a system, you have a controller, and these all work in a feedback loop. And the transportation system today is not that different. And so what I'd like to do over the first part of the talk is walk you through how the transportation system works, where the data comes from, where it goes, how it's processed, to give you a sense of the challenges that we see happening today. So if you think about this system dynamics and what the system looks like, anticipating onto next week's when you are going to go to Thanksgiving and going to hit Thanksgiving traffic, to understand the complexity of traffic, there has been decades and decades of research that has focused on how to build models of how people behave on the road, whether they're on freeways, whether they're on arterials. Of course, none of this gets used unless you have data. And if you think about the sensing data that the public infrastructure agencies have built over the last decades, these are very primitive and very insufficient in terms of coverage. Whether these are loop detectors, whether these are cameras, radars, tubes, or anything else, maybe 10% at most of the transportation network is covered by these. And even though that generates huge amounts of data, it's very insufficient in terms of what you would want if you want to monitor traffic in real time. If you think about control, the situation is also not that different. I mean, think about where you can be controlled where you're on the road. There's traffic lights, there's metering lights, sometimes there's tolls which are regulated. You get your information from signs that might alter your behavior, and some restricted access. For example, if you think about the I-210 corridor in California, in Los Angeles, this corridor every day sees tens of thousands, hundreds of thousands of people drive through it. But the number of control points to control flow on this network is 450 assets. Essentially, there's 450 traffic lights that you can use to control the flow of the thousands of people that drive through this corridor every day. And that's very little. But that's what's at the disposal of the agencies in charge of it. And so part of the talk today would be how we use all the data we have, and in particular mobile data. How do we use the computational platforms we have, in particular cloud computing and HPC, to provide better mobility to people using this network? And for this, there are a lot of questions that are of interest, in particular the question of state estimation. With such little sensing, what do you do to estimate the traffic? And then forecast. How do you build a model, a statistical model, machine learning model, that will enable you to predict what traffic will be in 2 hours so you can control it better? What it looks like in the room of practitioners who are in charge of this traffic is essentially dashboards that depict over time and location traffic. And when people are controlling traffic, they look at this, and this is the time at which they're looking, and try to figure out how to do real decision making. And we'll see throughout the later parts of the talk that this decision has almost nearly all the time a human in the loop. And forecast is a set of statistical models that, in a sense, predict where people will go, where they're coming from, and you can see in forecast models that there's usually a peak time in the morning, there's an even bigger peak time in the afternoon, and these get fed into a model that can be used by practitioners to control traffic. These all usually get fed into an optimization module. Why? Because we try to make things better and because things are optimized. So in a dream world where traffic flows well, what a traffic practitioner would like to see is something where everything is green and traffic is just flowing smoothly. And we'll know that's, of course, never the case. And so at the core of it, and probably for the many years to come, there still is a human in the loop. And when you take a flight, people don't debate that there should be a pilot. Well, when you control a city like Los Angeles, people don't debate that there should still be humans figuring out what to do because of the complexity of phenomena. So if you've seen movies like The Italian Job or others, you've probably seen these command center. It just looks like air traffic control center, except it controls your city. Every city has it. Denver has a big one. What these are essentially traffic display with people making decision onto how you're going to control the hundreds of assets that you have at your disposal. And there's a set of rules for it because you cannot do anything. Just like you can't just fly any aircraft the way you want, you cannot control the city any way you want. There's a bunch of playbooks and through operator interfaces, a set of scenarios that the optimizer is taking from. And that's where the computation comes in. Because to sort through these millions and billions of scenarios that are possible in the way you will control the traffic, essentially you have to solve very large-scale optimization programs over a very large-scale network in real time, keep resolving it as the data changes, and that's part of the story I would like to tell today. So the first thing I'd like to talk about initially is demand inference. In order to manage your traffic well, you need to know where people are coming from and where they're going. And so the revolution we've seen over the last couple of years is essentially with the explosion of smartphones, without even logging into GPS data, just by knowing which cell tower each of your phones is talking to, you already can get a very good sense of large-scale mobility patterns. Things like cities like Los Angeles have hundreds and hundreds of cell towers. So if you can know every couple minutes the approximate location of people within a couple hundred meters and track this throughout the day, it's fairly easy to build statistical models using convex optimization. So simple models to essentially find best fits of these parameters that can give you a sense of what these mobility patterns look like. So for example, every day when you're going through an area and you're talking to anybody on the phone, or even if you're not using your phone will be connected through cell towers. These locations get recorded. For example, companies like AT&T, which have around 40% of the US population in California, get 40% of people's location in real time. Now, this location is approximate. It's within a couple hundred meters, but that's enough to extrapolate to the rest of the population and figure out what people are doing. For example, this is someone traveling through the city of Los Angeles. It's not perfect. You can see that at some point the signal jumps, and that's because essentially the cell tower is probably a bit further. But in terms of understanding what that person is doing, that's enough. And statistical model can enable you to figure out that this is happening actually throughout the day. And this is an example of a FedEx truck that is delivering packages. This is an example of someone who goes to work, goes shopping, and go home. And this is another example of someone who goes to work and goes home. So part of the contributions of mobility modeling at a large scale is essentially taking this data and building origin-destination matrices, which are essentially mapping where people live and where people go, and from that, build network models that enable us to compute network loading. So if we know that on a Friday, usually given there's a bowl game here and it's raining and it happens to be in the winter, then we have a lot of statistical data that enable us to figure out what are the demand on the roads and where people are coming and going and what time they're commuting at that day. And from that, you can compute the network loading. So part of the work that initially was done in this area is essentially trying to understand how to come up with these large-scale models. It doesn't tell you how traffic flows in your street, but it tells you how traffic flows through your area, which is one of the inputs you need to feed these models at scale. Of course, if you try to regulate things at a local level, you need to do traffic estimation. That means you need to be able to predict or to compute and assess at a very fine grain the speed of people, the length of the queues at the traffic lights, the extent of traffic jams on the freeway, and that's a much tougher computation. And so what that means is that in terms of computation and using the standard representation of traffic engineers, if this is time and if this is location, what you're trying to construct is a picture throughout the day. The level of color in the picture indicates the speed. This is time and this is location. And essentially, if you can reconstruct that entire picture, then you have a notion of what traffic looks like. If you have this, then you have the extent of traffic jam within a couple of meters, and that's what you need to control traffic. So imagine you had nothing. So essentially, the inference job is you want to reconstruct the picture here in color, but you don't have data. If you can sample data at given location by putting sensors on the road, essentially what you have is you have data along the black lines. If you can estimate data, say, in the middle of the night, because you know that the freeway is nearly empty, you have data along the green line. If you can track a few vehicles, you can sample the data along these trajectories. And if you don't track people for privacy reasons or because you don't want to do it, but just re-identify people, for example, oh, that's the same person here and here on the freeway, that means you have an indication that this data and this data correspond to the same person. So the job of inference at scale is essentially from these very sparsely collected data from smartphones, data from all these sensors, how to reconstruct at large scale the patterns of traffic. And the way this is done is by having mathematical models, partial differential equation models, so just like people doing HPC at scale for computational fluid dynamics have essentially solvers that solve Navier-Stokes' equations or variations on Navier-Stokes' equation. If you do this for traffic, essentially you do this with a Hamilton-Jacobi equation. So that is our constitutive model of traffic. And then that's essentially what goes in that box that I showed earlier. And then if you sample it at a given location, then you can sample the value of the function. If you sample it at a given time, you can have an initial condition, just like in PDE modeling. And then if you sample a trajectory, for people who are interested in oceanography or in environmental sciences, essentially you're sampling a Lagrangian trajectory, just like people putting balloons in the atmosphere or putting floating sensors in rivers. So the job of inference is essentially the reconstruction of the solution to that PDE, which is shown here, given the data you have. And part of the contributions to be able to run this at scale, in particular on the HPC, is to put this in a format that can be scaled easily. And it turns out that these formulations with Hamilton-Jacobi equations lend themselves very well to convex optimization programs, which we know can be decentralized quite efficiently on HPC. And that's part of the work that we do. And so typically, to show you how it works is, if you had access to 2% of the driving population, and each of these people were sending you a point of data with their speed every 2 or 3 seconds, this is what data would look like. So essentially, you can read traffic, you can read traffic jams. And you can see this big traffic jam here, and you can see it's dissolving and it's reappearing in the afternoon. Now imagine you only have 1% of this data. So now this is what it looks like. The job of reconstruction is much harder. And typically, what this convex optimization program can do is that they enable you to reconstruct data fairly accurately from the very sparsely sampled data. So this is if you had 2% of people equipped with smartphones. And so in a sense, when we started that project nearly 10 years ago, this was the game. At the time, when only a few people had phones, then, and long time before the Android emerged and the iPhone became one of the standards, what people were trying to do is reconstruct traffic maps like this from these phones, which you can see are pretty vintage, and this was one of the first program we do, and within a few years transformed this on the left, which is the way you used to get your traffic information 10 years ago, into this, which all of you have on your phone today. And this essentially is now powered entirely by mobile data. So the story I'd like to tell over the next 10 minutes is how we got there, what are the algorithms underlying this, and what problems it's causing today. Because if there is traffic today, in a sense, this information at scale has not solved it, and in some cases, it actually has made it much worse. So initially, when we built our first prototype nearly 10 years ago of an app collecting that data, what we had to do to convince people that things work is we had to run experiments with hundreds of cars on the freeway, each of them carrying a phone, to show that at that level of granularity. So here is an example of a demo we did in 2008. With these amount of collectively transmitting devices on the road, you were able to reconstruct traffic with a fairly decent accuracy. And typically, later on, when we scaled and started collecting data from private vendors, we started to demonstrate how you could do things at a much bigger scale. So for example, the movie you see here is 30-second sample GPS data for the city of San Francisco, collected by 500 taxis, sending you 2 data points a minute. You can see that if you let this movie play for a while, after the whole day is played, you can essentially draw the map of the city. And that could seem a lot of data. Imagine today, Uber has 40,000 drivers registered for the city, and each of these drivers sends 1 data point every second to Uber, because that's how you see the Uber vehicle moving on your screen when you order it. So you can imagine, from looking at this amount of data, the data available today to collect traffic information. This is another example below of the data collected in a few hours for the corridor I was showing before. And so what we built, and what a lot of other companies built, and this is what Google Maps is running, what Waze is running, what Apple Maps is running, is essentially a system which has a lot of feeds, ingesting data, cell phone data, sensor data, and many others, putting this into filters that go through models that feed the estimators and predictors I've just talked about before to show traffic information that essentially enables the system to broadcast this information in real time. And so initially, when we launched this program, we wanted to show the difference of a system that is not using this data with the system that is using this data. And at the time, Google was not using this data. And so what we were trying to do is benchmark how much better you could do with the cell phone data. And so this movie, which is an accelerated version of traffic, because watching traffic is fairly boring, shows you essentially that with the presence of smartphone data as opposed to just sensor data, you can essentially give traffic information up to 15 minutes earlier than otherwise. And this is something that we all collectively have today on our phone. It's free. Every major provider has either their own traffic information, or they have Google, or they have Waze, which is the same, or they have Apple, and it's a very mature field. So the problem I'd like to talk about now is that I'd like to see what happens when all of us have this information. And so this is where it goes into heterogeneous games. When you turn on your phone in the morning and you punch in your destination, what it does is it searches a huge graph with a glorified version of Dijkstra, improved A-star, and it essentially finds the shortest route for you, where shortest is either based on statistical models or, in many cases, just the way traffic looks now. So for example, if you're driving from Berkeley to this other university on the other side of the bay, it will give you the shortest path, and it will probably give you another 2 paths which are nearly equal to you. And what that means is that it essentially changes the dynamics of the system. Because now, what it has done, it has created a feedback loop around the dynamics. 10 years ago, you knew your way to that university, so what you would do is you would essentially know that on Monday morning, it's better to use the Dumbarton Bridge and take that bridge. But today, you don't even think about it. You just hit the road. This morning, I left my home to go to San Francisco Airport, and the Uber, which was the guy was happening to use Waze, figured out that he should use Bay Bridge because Bay Bridge is the fastest. So essentially now, there is a feedback loop within the dynamics, and whoever is controlling traffic lights or all the other ways to control traffic has no access to it. So anybody who has built any controller knows it's a very bad idea if you have a system and you have a controller that is built for a different system. It's like you have a 747, but you're putting instead a controller for a jet fighter pilot aircraft, or vice versa. Not a good idea. Now, maybe people think, well, that's kind of an academic problem, and it's not true. It doesn't really manifest itself. So here's a few headlines that are interesting. Long time ago, many companies try to advertise the fact that if they give all of you the shortest path to where you want to go, it's good for society. It's good for traffic. So you can see the mayor of Los Angeles making big announcements, and people buying in that, you know, if everybody's going to use an app and everybody gets their shortest path, it's good. Until more and more people started to use it. So that gets us back from 10 years ago to now. And then suddenly people started to figure out, oh, that's strange. I see a lot more cars in my neighborhood. And people started to get upset. And if yourself have noticed in recent years, and I'm going to flip through this because it's happening everywhere, that you have more and more traffic in your neighborhood, well, there's a reason for it. It's because all of us are now using a shortest path algorithm and going through streets which were not initially designed for this. So by giving more information to people, essentially, the question is, have we made things worse? And you can see it's getting really graphic now. People are really upset about this, to the point that people started to resist by posting signs on their streets, don't come to my neighborhood. This is bad commute. Or posting fake detour signs to confuse people going through their neighborhoods. Or even paying senior citizens that live here to walk with their phones on the street pretending they're a car stuck in traffic, because that will spoof the algorithm. In fact, there is a lot of manuals on the web, you can find them, that show you how to spoof the app. So now that changes the information, because the information makes people upset and people want to change the information. And to change the information, there's a really good way. You could make the traffic even worse. And so what urban planning design people have done is, like, they cannot sue Google or Waze. Waze or Google together have probably 1,000 attorneys. And the city of Pasadena, just pick one randomly, have probably 2 lawyers to defend themselves. So what do they do instead? Well, build street bumps or turn restrictions or change their traffic light signal timing plans to make things worse. Because if you make your own traffic worse, then the algorithm will ultimately learn to not get people through your neighborhood. This is where information has gotten us today. And so it's interesting because now things get even organized. The politicians and elected officials are getting really concerned about this because their constituents are pretty upset. And we start to see some class actions or some, at least, attempts to resist in a more institutional manner. And so this is where our story begins today. This is happening everywhere. In fact, if this has happened in your neighborhood, send me an email, because we are collecting a lot of data to try to understand what happened. These snapshots here show you the newspapers where we have seen hit the news. We have seen this phenomenon hit the news. So if it makes it into the paper, it's got to be a really a hard instantiation, but it's happening everywhere. So how do we learn? How do we use machine learning? How do we run algorithms at scale to try to understand this problem and how to fix it? So there is no good theory for it. It's something relatively recent. Before I dive a little bit deeper into the science of it and trying to understand what happens, let me show you a movie that explains why this is happening and why it's not that easy. So what you see in this movie, which I'll play in a minute, is twice the same scenario. One where nobody in the bottom is using any information. You can think about it as, life 10 years ago, or you have no more battery, so you have no way to figure out traffic information. And here, a scenario where 20% of the population uses the same app, which is not far from reality. I mean, think about the correlation of car ownership and phone ownership in the US is nearly 100%. Everybody who drives with a car these days has a phone. And then probably every 5th person is using an app. And how many apps are there to look at traffic? Google, Waze, Apple, Inrix, and maybe a few others. And so you'll see the difference of what happens without information below and what happens with information above. So let's say, this is traffic micro-simulation. So let's say there's an accident. The accident will create a lot of traffic. You can see it here. The traffic backs up. Okay, I'm sure you've been in a traffic accident before. I mean, not yourself, but stopped because of a traffic. So what does the app do? It tells you to leave the freeway because you should try to figure out another route. So if you have the information, you leave the freeway. If you don't have the information, you stay on the freeway. Ultimately, the accident is removed. It takes, on average, a few hours to the California Highway Patrol to remove a big truck from the freeway. The freeway traffic reestablishes itself, and now the road clears. The problem is the app has told 100 people to leave the freeway. So that has created its own traffic jam. because the off-ramp gets clogged. And I'm sure you've been in that situation. Like you see a clogged off-ramp, that's probably happening because everybody wants to leave the freeway just like you're doing. And now, you can see above, there's a lot more congestion on the upper plot because you have all these hundreds of people on the side streets which are absolutely not designed for it, going through intersections which don't have the capacity to process this extra traffic. And therefore now, not only you have congested the freeway, but you also have congested the side streets. So this is an example of a computation run on MSUN. MSUN is a micro-simulator. By the way, the movie continues, and you can see that it also screws up the traffic on the parallel connectors and perpendicular connectors. So this is an example where more information is actually worse. And so I think this also illustrates the fact that these processes are fairly complex. They're not easy to understand, and they're also not easy to explain. And so what we'd like to do with this now is create mathematical models so that at least one can create a world in which app providers, which have no incentive to give you anything else than the selfish good for you, which is how do you get to work as fast as possible, how can we get them to collaborate with public agency who manage the network? And so it's not that easy. And so let me show how we model this. Essentially, at the core of it is this feedback loop that did not exist 10 years ago that is here today. And so what that means is that in understanding how to compute these models, what we have to do is we have to incorporate an extra layer saying that now people have the information, so they will not act as predicted by the statistical models. The statistical models are great. They show you that on average this happens, but when an accident happens, you don't have statistics, because there's no statistics of 3 lanes being blocked at post mile 3 of this freeway, because this is the first time it ever happened. Even though there is an accident a day roughly on I-210 in California, there's not enough accidents to have good statistical samples of accidents and their effect on traffic. So this is where the statistics will keep failing. But we have to understand what the flow models tell us to counterbalance for the fact that now information is given to people that don't fit in the statistics, and that's going to affect traffic. And so the type of models that Juliette Origo-Moreira has built at LBNL using NERSC do exactly that. So these are models we run on NERSC using HPC, in which using simple static analysis of what happens, we can run at scale computations where we can simulate any proportion of the population using an app and the effect it has on traffic. And so it's very interesting because we can run these models at scale. We can also run these models as demand increases. In the Bay Area, for example, there was a small startup called Google when I was at Stanford, which had 10 employees. Okay, Google today on the main Mountain View campus probably has 30 or 40,000 employees. You can imagine that completely changes demand. Treasure Island, in 3 years, will have 18,000 additional apartments. That means enormous amounts of traffic on Bay Bridge. So to run these things at scale, it's not an easy problem. And these are the type of things that we do at NERSC, where we can fairly easily, using convex optimization and algorithms like Frank-Wolf, parallelize computational techniques to compute such solutions. And the type of results we get from this analysis is actually quite nice, because you can start to explain what's happening. So taking a very short and simple run that everybody can understand here. If you take this segment of Pasadena, where you have the I-210 freeway here, and say 2 parallel streets, what's going to happen is that if nobody had any information, say 10 years ago, nobody would leave the freeway, because you don't know what traffic is like ahead of you. You don't even know if it's better to take a side route. So you'll have a pretty significant travel time here. And travel time on the arterials would be pretty good, because nobody's taking the arterials. And then you can view this axis, the proportion of people using the app, as history moves forward. It's 10 years later, and now there's maybe 20% of the people are using the app. 20% of the people are going to figure out, oh, I should leave the freeway and take the side street, because it's actually better. And of course, the more people leave the freeway, the better travel time gets on the freeway. And the more people take the side streets, then the worse it gets on the side streets. So the first street gets congested, the second street gets congested, and ultimately, at some time in history, the two got nearly the same. And that's called a Nash equilibrium. If you've seen the movie A Beautiful Mind with Russell Crowe, that's an example of a Nash equilibrium. It's like if everybody is doing the selfish thing, if everybody is doing what's best in their interest, in a way that so there's no incentive to deviate from this, because if you deviate from this, you sacrifice yourself for society. While you end up in what's called a Nash equilibrium, which is a fairly known concept in game theory, and people know, and this is John Nash won the Nobel Prize for this, that this is not optimum. This is what ubiquitous traffic information has enabled at scale today. So 10 years ago, when we were building the first traffic apps, in a sense, we were thinking, well, this is helping because it gives more traffic information. And as long as only a few % of us had these smartphones or were using it, well, great. We got a better deal than the rest of the planet, and it didn't really affect the rest of traffic in a significant manner. But today it has, and this is why all these claims that if you are giving people good traffic information, well, things will get better are completely wrong, because they don't make things better. They just drive things to a Nash equilibrium, which is an interesting phenomena that we can observe every day if we're selfish. And so the thing which is to remember here is that today the way traffic information is managed is not collaborative. Google and Apple will not collaborate. There's no incentive. And there's also no incentive for any of these companies to give you something that is not selfish. Because if I'm an app provider and I give you a travel time that is good for society, but by which you lose 10 minutes on your commute, the first thing you're going to do is delete the app from your phone, because that app is not good for you. So essentially, it's a situation where not only we're all competing against each other for capacity on the street, but then all these companies are also competing against each other because there's no incentive in collaborating. And that's what we see today. This is not only a single feedback loop within the dynamics, it's a set of different feedback loops in the dynamics. And the problem is that these feedback loops, they keep changing over time. The information you're getting on your phone today is much better, or at least is different than the one you were getting on your phone 5 years ago or 5 months ago, because these algorithms themselves keep learning. So you can think about this problem as an environment in which every day these app providers collect huge amounts of data. And every day they learn from this data how to route people differently. And these routing schemes, they change over time. And you probably noticed recently this app enables you to find better shortcuts or different shortcuts. That's the learning algorithm happening inside these companies. Of course, we don't know what that learning algorithm is. It's symbolized here by this equation in which every day there's an outcome of the routing process that provides some latency function, and the next day the routing algorithm will change. So the type of work that is interesting to do in this field is understanding, can we make some assumptions on the learning? And if we can model the way these companies learn, because we don't know, and we're not going to get access to their learning algorithm unless we work for them, can we say anything about where that process goes? And so typically what that means in economics term is that we'd like to understand over time, as all these apps keep learning, what it drives the system to, and can we prove anything about the convergence to an equilibrium? And so this is an online learning model in which, depending on the assumptions you make on the learning laws happening under the hood, you can prove different things. So for example, if you make the assumption that the learning algorithms used by these companies have very general assumptions, that they're just no-regret algorithms, then at best you can prove that the convergence to this process is, on average, to a Nash equilibrium. If you do machine learning, it's good because this is also a good algorithm for learning, but average doesn't help you in traffic. If you know that on average the system does something, it really does not help you manage traffic, because it's very easy to construct examples where on Monday this freeway is super congested, so on Tuesday everybody takes the other freeway. Now that super freeway is congested on Tuesday, so on Wednesday people revert to the first freeway, and so on and so forth. And we see this happening in traffic. So if you make more refined assumptions on what these algorithms might look like, then you might end up with better convergence rates. So if you make the assumption that the learning process under the hood is a hedge algorithm, which is a very commonly used algorithm in finance, then you can prove then you can prove convergence almost surely. What that means is that now you know that the system will converge to a Nash equilibrium. And if you make even stronger assumptions that the process of learning is a decentralized process from convex optimization by doing mirror descent, using the Bregman divergence, then not only you can prove that the system is converging, but you also have rates of convergence. So the point here is to show that if you're an operator, you have no idea what these apps are doing. If I'm in charge of the Denver traffic, I have no idea what apps people are using. I have no idea what algorithm runs behind these apps, and I have no idea how the app users or how the app providers are updating these algorithms. So essentially, it's a set of Matryoshka problems that I have to reverse engineer. You, most of you, a lot of people will behave selfishly and will want a faster route, whether it's good for society or not. That means essentially we are all running a closed feedback loop to essentially find what's best for us. That creates a certain dynamics that is not possible for people to measure or very hard to model. That itself gets embedded in this whole control scheme, which itself keeps changing day after day as the algorithm learn. So you can see this kind of multi-layer set of learning problems. And this is going to affect our lives quite significantly. I mentioned earlier, so the smartphone explosion, that's what happened over the last decade. Everybody has a smartphone, and that's a reality of life. Demographic growth in the US is also very big. I mean, we're going to reach 50 million people in California in not so long. Google was a startup when I was a student. Now there's a huge campus. Treasure Island, I mentioned, is going to be 18,000 new apartments. Tesla opened a factory with a couple thousand people. These things completely affect our demographics. So understanding how the system learns from it is quite complex, and having the ability to run algorithms at scale, like Juliet is doing on the NERSC platform at LBNL, is essential to have a good understanding of these phenomena. And the reason why these phenomena are hard is because, A, the dynamics inherent to these phenomena are inherently nonlinear and distributed. Just look at traffic. It's not easy to model traffic. The control is often decentralized because even cities within their own jurisdictions don't collaborate. There's no unification of infrastructure. If you take the LA basin, there is a mosaic of different systems that don't talk to each other. Obviously, people are non-collaborative. Companies are non-collaborative, so it creates a non-cooperative game. And then you have these feedback loops that involve humans. And that's why things are fairly complex. So this is not just in traffic. This happens in many other phenomena. But I think the computational challenges that are posed by these problems are quite interesting from a theoretical standpoint, because there is a whole range of open problems to be solved. And then the corollary to this is that the computational aspects that go with the computation of the numerical solutions to this problem is also non-trivial. Let alone that if you want to run a computation at the scale of LA, it's a huge network. So to finish this talk, I'd like to talk a few other applications that also have been implemented on the HPC at Berkeley, at LBNL, over the years, that also benefited from this ability to distribute computation quite efficiently. One of the first thing we were doing back in the day was essentially using smartphones to monitor earthquakes. And so we were one of the first to build a smartphone app that was using the accelerometer to monitor seismic vibrations. And today, that app is in the T-Mobile App Store, and the Seismo Lab at Berkeley has been running it for several years. Another thing, which was actually the first infrastructure system that we try to use as a benchmark example for how to run distributed computation for infrastructure at scale, is doing data assimilation using floating sensors on NERSC. At the time, and this was like many years ago, we were using already a couple hundred nodes of the NERSC cluster, and what we were using is we were using these floaters that you see here. So these are essentially units which have a smartphone in it that it can essentially transmit a lot of data to a backend from the flow. So you can see the speed of the water, you can see the water quality. They also have motors, so they can do distributed measurements. And so it's one of the many examples of using streaming data and running inverse modeling algorithms, just like the one I showed for traffic. This one is using shallow water equations to be able to predict in real time the state of large-scale infrastructure systems. And then last example before I finish, going into the future, the thing which is really exciting that we're doing now, and this one is more a cloud-based system, is we're running deep learning algorithms to understand faults. And so here, it's a fairly different problem, but uses a similar architecture in which we're using deep learning to learn what a fault looks like. And the specific case we're interested in is Alzheimer's patients in memory care facilities, understanding how we can use that data to predict faults and do alarms in real time. Falls is the #1 cause of mortality in memory care facilities, so it's actually a fairly big problem in the US. And so with this, I'd like to conclude by saying that over the last 10 years, infrastructure systems, whether they're home infrastructure, whether they're city infrastructure, or whether they're even bigger infrastructure, have evolved a lot, just because the type of data and the amount of data we're getting from various sources, including crowdsourcing, have really changed all the paradigms of real-time computation for inference and control. And so there's lots of years to come in which we can really improve a lot of the efficiency in which these infrastructure systems are run by getting better understanding of the physical processes underlying this infrastructure and better understanding of the computational processes to compute the corresponding solutions. And so with this, I'd like to again thank you for the invitation to talk today, and I will be very happy to answer any question. Thank you.
We have some time for some questions, and maybe I can start. What do you say when people ask you which traffic app to use?
Oh, what do I tell people which traffic app to use? I think most of the traffic apps use the same algorithms, which have evolved over time. I think initially they used posted speed limit, then they used instantaneous measurements, and now they use statistical forecast. I mean, I can't recommend one more than the other. I think they're all equally good, but I think what's really important is, understanding how the app providers will in the future try to interact with public agencies in a way that the effect these apps have on everybody's mobility become positive.
Okay, that sounds fair, thanks. Microphone 3.
Thank you for a very interesting talk. It seems like the fundamental problem is that we're all being selfish, and there's no incentive not to be selfish. With all the simulation that you can run, have you done any computations to see if, for a given situation, instead of achieving the Nash equilibrium, you actually were able to direct traffic, how much would be saved? How much faster would people, on average, actually get to the destination? And is there a way to use that as a feedback into the system to make people less selfish?
Yeah. So these computations that steer the system to a system optimum are things that we routinely do, and you can show that on some commute routes you can improve commute time by up to 20% or 30%. So that's a huge amount of time if you are on long routes. The real question is how you do it. So the simplest way to do it is you could send people fake information, since, like fake news, you could send them fake information on their phones. That worked very well. Obviously, that would be problematic. So more seriously, there's really two ways. There is incentivization, and then there is penalization. Penalization, we all know it, tolling or restricted access, and that works really well. So for example, you can see the influence of a toll on a bridge. If you raise the toll, will steer traffic on the bridge. Singapore has implemented congestion pricing many years ago, and it works well. London has cordon pricing Okay, there's a lot of equity issues with that because you have to figure out which populations get affected, and usually the ones that get affected are the ones which are the least wealthy for various reasons, but that works. What works less well is incentivization. If I give you a free cappuccino for an extra 5-minute detour or an extra 10-minute detour, given your consulting rate, you probably wouldn't take it because a cappuccino is not worth your time. So at the end of the day, when things become really bad, like the 101 corridor in California, tolling won't work either because you could put a $20 toll to use a lane or a $40 toll. There's a lot of people driving Teslas or Rolls-Royce or Ferraris who would still take the road and still congest it. So when you hit that border, which we have hit in California, the only alternative that remains is restriction of access. So for example, if you impose that specific lanes on freeways are HOV 3 or 4 or 5 or 6, that means like 6 passengers per vehicle, that's the only way that you can really enforce smoothness of traffic. Because now it forces people to essentially carpool or take a form of transit or a form of rideshare or any kind of other system where you force people to bundle together. So it's a graduation between free cappuccino that never works, to tolling that works, to essentially when things get too bad, strong and harsh regulation, which is the only alternative left to governments, which is very hard politically.
That's not a very rosy outlook.
I'm sorry, but it is unfortunately, it is a fate of urbanization, and I agree with you.
So we're running out of time, but I'd like to maybe take 1 or 2 more questions. So maybe from microphone 1.
Thanks. So how do you think that self-driving cars will fit into this, where maybe a whole company owns 40% of the cars and you don't own it, so maybe they have an incentive?
Yeah, oh, no, excellent question. There is a really good article by Don McKinsey from UW in Seattle, which has shown that with self-driving cars, you could decrease the energy, so congestion roughly, by 90%. In the best case, that means essentially eliminate 90% of the congestion, or you could increase the congestion by 200%. So how does it work? The 90% reduction in an ideal world is collaboratively all the vehicles self-optimize, and that's doable. The algorithms are already there, so all you need is the proper jurisdiction to enforce it. For example, in the Middle East, we see cities which will have self-driving districts being planned over the next 5 years. If you have a self-driving district where essentially the district takes over the routing of your vehicle, just like air traffic control, then you can have this 90% reduction. That's the paradise. And then the hell is 200% increasing, where now you have a bunch of empty self-driving cars on the freeway because I'm going to send my car pick up my daughter at school. So now I have an empty car on the freeway to pick up my daughter at school. And then there's no parking, so the car is going to hover and, you know, essentially continue looking for a spot in the city until it's going somewhere else. That's hell. No regulation, and, you know. So anything in between is possible. And this is a perfect example of why regulation will be extremely important, because if you want to push this even further, now that your car is self-driving, you can afford to double your miles, because you can afford to leave twice as fast from your work and sleep in your car in the morning, because your value of time is worth it. Your value of time is probably more expensive than the gas or the electricity to do it. So if you can eat or work or sleep in your car, you can double your mileage, and that increases congestion even more. So how do we steer a self-driving world to an equilibrium point where we're closer to the minus 90% than to the 200% increase in congestion? That's the real question, and access and regulation is, in my opinion, one of the few things at the disposal of public agencies to make this future brighter rather than gloomy.
I know you have a flight to catch at the airport. Do you want to take any more questions?
I'll risk one more question and then I'll run.
Okay, maybe from microphone 2 then.
Okay.
I was wondering if you had done any looking into a higher level of feedback loops where you have jurisdictions on the middle of a commute where they have a traffic impediment and are being routed through local communities there, causing political issues in that local community, that the local community can fix the impediment on the main commute route. Have you looked at that at all?
Yeah, and the main thing at the disposal of such communities would be tolling, because if you impose a toll to go through your neighborhood, technically you could route people around it. But there is a law in California, and I think it's pretty similar in many states in the US, which says that you cannot toll for anything that exists. You have to build it to toll for it. So it's a potential alternative, but then you would have to rebuild your freeway to be able to toll for it and control it, which is a complicated value proposition.
I'm looking at it the other way. If you have an impediment, if the lanes are cut down on the main road, and you now have a local political push to remove that impediment because it's causing a problem in the bypass area.
Yeah, that's something we see happening sometimes. And usually it fixes problem locally. So redesign an exchanger or redesign a traffic signal control plan. And usually it helps, at least temporarily and locally. What it will do ultimately is it'll displace the problem because another bottleneck will appear somewhere else. And then there's an even higher level of feedback is that if you improve things too much, then latent demand comes in, because, oh, now somehow they've fixed the freeway, there's no more traffic jam, then more people will start driving. That's something known in economics that is even a bigger problem on top of it.
So I know there are additional questions, but I apologize that we have to end here. Let's thank Dr. Bayen for his fascinating talk.